Welcome to the second part of the tutorial on casting that we are discussing in this week. We are in the course Basics of Mechanical Engineering 2. This is Manufacturing Processes course. I am Dr. Amandeep Singh. We will discuss the casting further in this lecture. Let us now try to review the sprue and gate design what we have discussed in the previous lectures. For analysis, we use balanced Bernoulli's equation, which is the pressure head, the velocity head stays constant over time, the sum of the heads. Now, assuming P1 is equal to P3 and at level 1 is maintained constant, so V1 is equal to 0. You can see this figure. Energy balance between the point 1 and 3 gives, between the point 1 and 3 it gives GHT is equal to V3 square by 2, which gives me the value of V3 as under root of 2 GHT, where V3 is my velocity at the sprue base. This is velocity at sprue base here, or we can also say that this as Vg, which is velocity at gate. This is gate entry. G is the gravity coefficient. HT is our height of the sprue. This height HT is given. Let us try to see the problem statement. A down sprue leading into the runner of a certain mold has a length of 175 millimeter. The cross sectional area at the base of the sprue is 400 millimeter square. The mold cavity has a volume of 0.001 meter cube. We need to determine the velocity of molten metal flowing through the base of the down sprue in millimeters per second. The units are given. The volume rate flow in millimeter cube per second. The time required to fill the mold cavity in seconds. Let me try to take all these problems one by one. First thing is the velocity. Just to recall, the velocity equation we saw here, V3 is equal to under root 2 GHT. Let me just put same here. I will call the velocity as V, and if I try to draw a small figure, so this is the sprue. Let me say this is 0.1, this is 0.2, and this height is given. It is given as 175 millimeters. This is my H. Right. We need to find the velocity at point 2. I will call it at V2. It is also given the cross sectional area at the base of the sprue is 400 millimeter square. That means this area, it is 400 millimeter square. To find the velocity, velocity is under root 2 GH, which is equal to under root of 2 into 9.8, that is meters per second square, into the height. We will put height as 175. I need to compensate this, so I need to put 1000 here because this is to be required as millimeters per second. To convert 9.8 meter per second square to millimeters, I have put this 1000. So, this value comes down to 1853 millimeters per second. So, this is problem 1 solved. Problem 2, the volume rate flow in millimeter cube per second. For the volume rate flow, I need to find Q as my volume rate. Let me say Q is my volume rate flow. Q is volume rate flow, and Q1 is equal to Q2. The volume always stays constant. What is the total volume? Volume that flows through the entry of the sprue, the exit of the sprue. So, which is, I would say Q is equal to A into V, where V is my velocity, or I could even say Q1, that is equal to A1 V1, and Q2 is equal to A2 V2. Since Q1 is equal to Q2, I will put it as A1 V1 is equal to A2 V2. We call it as continuity equation. Now, this value of Q2 is equal to A2 into V2, A2 into V2. Let us just see, we have been given this A2, the area here is 400 millimeters square, and V2 also we have calculated 1853 millimeters per second. Let me try to now find the Q, the volume rate. So, this is equal to (400) into 1853. So, this is millimeter square, this is millimeter per second, it becomes millimeter cube per second. This comes as 741200 millimeter cube per second, or 7.412 into 10 raised to power 5 millimeters cube per second. The second problem is also covered. Third, time required to fill the mold cavity. Time required. Time required, we will see the flow here is given. Now, we can see the flow is calculated, flow rate is calculated here, Q2, that is equal to 7.412 into 10 raised to power 5. Let me calculate the third part of the problem here. Time required to fill the cavity, let me say. So, since we know Q is equal to area into velocity, right, I am putting it as a vector quantity here. So, therefore, this is equal to area into length by time. To find my time, I can just say time here would be area into length by Q, which is equal to volume of mold cavity over the volume flow rate. Which is equal to 10 raised to power 6, it is the volume of the mold cavity. Volume flow rate is given or it is calculated, that is 7.412 into 10 raised to power 5. This gives me the time as 1.35 seconds. The volume 10 raised to power 6, how has it come? It is given here in the problem, the volume is 0.001 meter cube. So, this value is 0.001 meter cube, this volume is here. So, this if I convert it into millimeters, it will turn as 10 raised to power 6 millimeter cube. So, this was one of the problems in gate and sprue design. Let me see another problem where the units would be in liters per second, and we will use the complete Bernoulli's equation where the potential had, the pressure had, the velocity had, all we will use here. So, this is a problem statement where it is given, it says the flow rate of liquid metal into the down sprue of a mold is 1 liter per second. The cross sectional area at the top of the sprue is 800 millimeter square and its length is 175 millimeter. What area should be used? What area? should be used at the base of the sprue to avoid aspiration of the molten metal. Area is to be found or is to be calculated in millimeters square. Now, for this problem, we have been given 1 liter per second. Now, we know that 1000 liter is equal to 1 meter cube. Let me put it in a way here, 1000 liter is equal to 1 meter cube, which means 1 liter is equal to 10 raised to power minus 3 meter cube. Fine. Now, the flow rate here is 1 liter per second. This is our Q. Or I can put it as 10 raised to power minus 3 meter cube per second. Millimeter square is required in the final problem or on the answer. So, this will turn to 10 raised to power 6 millimeters per second. Again, the sprue is something like this, with height given as 175. The area here A2 and A1, it has been given area at the top of the sprue is 800 millimeter square. A1 is 800 millimeter square. From the continuity equation that we used in the previous numerical as well, A1 V1 is equal to A2 V2 is equal to the quantity Q. This is all same, which means A1 V1 is given as here 10 raised to power 6 millimeters per second, which means A1 is 800, 800 into V1 is equal to 10 raised to power 6 millimeters per second. This gives me value of V1 as 10 raised to power 6 by 800. This is equal to 1250 millimeters per second, the velocity at 0.1 V1 V2. Now, using Bernoulli's equation, with all the assumptions which are there in Bernoulli's equation, that the flow is incompressible, it is steady, it is incised, all the assumptions of Bernoulli equation are now taken. Now, let us put the Bernoulli's equation here, which says the sum of the pressure head, the velocity head and the potential head are all equal. So, here to put it in the equality form and all the heads, P1 by rho g plus V1 square by 2g, that is the velocity head, plus Z1, all the three heads are there, the pressure, the velocity, the potential. This is equal to P2 by rho g plus V2 square by 2g plus Z2. One thing is, this is crossed here, since P1 is equal to P2 is assumed, the assumption of steady flow, and Z2, this is at base, that means Z2 is equal to 0. We are left with V1 square by 2g plus Z1 is equal to V2 square by 2g. V1, let me put the value 1250 square by 2g, 2 into 9.8, converting the units to millimeters, plus Z1, that is the potential head. I will put the value of Z1. Value of Z1 here is 175. This is equal to V2 square by 2 into 9.8 into 1000. So, from here doing all the transformations and taking square root of the value that comes after the subtraction and setting the equality right, we get the value of V2 as 2235.173 millimeters per second. So, this is the velocity required as it is mentioned in the problem at the base of the sprue to avoid aspiration. So, this is velocity at the base of the sprue to avoid aspirations, or I call it as aspiration effect. Now, they have asked what area should be used. Still need to calculate this area, that is at the base. So, at the base the area is to be calculated. So, using the continuity equation once again, or we just calculate A2 is equal to volume flow rate by the velocity, the Q2 or Q whatever you wish to put. So, this is equal to 10 raised to power 6 by 2235.173. So, I got my value of area as 447.4 millimeters square. I am going to put the same statement here. This is the area at the base of the sprue to avoid aspiration effect. This was an interesting problem statement where we designed the sprue, the area that is required at the base, the height was given 175, the flow rate, continuity equation and Bernoulli equation both were used. Let me try to see another problem statement which will give us more insights into the design of the sprue and the gate. In this problem, it is given molten metal can be poured into the pouring cup of a sand mold at a steady rate of 1000 centimeter cubes per second. We have got the value of Q. This is your Q. The molten metal overflows the pouring cup and flows into the down sprue. The cross section of the sprue is round with the diameter at the top as 3.4 centimeters. Diameter is given at the top. If I design a sprue here, this diameter is 3.4 centimeters. If the sprue is 25 centimeter long, the height of the sprue is 25 centimeters. Determine the proper diameter at its base so as to maintain the same volume flow rate. We need to find this diameter. Phi is required, that is question mark. This you can calculate using the similar setup. You will use the continuity equation. Q is equal to A1 V1 is equal to A2 V2. This part would be used. You will find the value of V1 from here. Using this value of V1 now, you will use Bernoulli's equation. You will say V1 squared by 2G plus Z1 is equal to V2 squared by 2G, similar to what I did in this problem, the previous problem. So, you will calculate the value of V2 from here. This value of V2 while putting into Q is equal to A2 V2, you will find the value of A2. So, this is step 1, this is step 2, this is step 3, and value of A2 that you will get finally is 4.043 centimeter square. Because this is area and it is circular sprue, we can definitely find the value of d pi by 4 d square is 0 A2, which gives me d, that is the diameter at the base. I will call it as d2. This is as 2.2688 centimeters. You can calculate this and compare your answer with the complete solution provided in the lecture notes. Let me try to solve another interesting problem where we will calculate the G factor. These problems are now something that you are conversant with. So, there are certain other problems like this. Before that, let me try to recall one more thing that we discussed in the last lecture. So, V is equal to V3 is equal to under root 2G HT minus H. If the sprue is designed in this way, where this is our HT and we have the height H. So, between 3 and 4, V4 is very small, between these 2 points 3 and 4. All kinetic energy at 3 is lost after the liquid metal enters the mold. So, these are certain assumptions which are taken to calculate or to design the sprue further. Now, here we need to calculate the G factor. It says a horizontal true centrifugal casting operation will be used to make copper tubing. The length will be 1.5 meter with outside diameter as 15 centimeter and inside diameter as 12.5 centimeter. If the rotational speed of the pipe is 1000 revolutions per minute, determine the G factor. Here we have been given the centrifugal casting system in which length is equal to 1.5 centimeter. The outer dia, we will call it as DO, this is equal to 15 centimeters. Then internal dia, inside diameter, I will call it as DI, this is equal to 12.5 centimeters. Rotational speed is given here, I will call it as N, this is equal to 1000 revolutions per minute. G factor, this is ratio of centrifugal force to weight, which is essentially representing how many times stronger the centrifugal force is compared to the force of gravity. So, we calculate the G factor as centrifugal force per unit weight. The centrifugal force is to be calculated from the given data and the weight is also there. I will put it as this is equal to Fc by W, that is weight. The centrifugal force here is mv square by r and weight is mg. This gives me v square by rg, or I can put the value of v as r omega. This gives me r omega square by rg, and this turns down finally to r omega square by g, which means my G factor now is r omega square. I will put it as r into omega, that is 2 pi n by 60 square by g, and here essentially r is equal to d by 2. We are talking about the outside diameter, therefore, r outside is equal to 15 by 2. This gives me my G factor as 15 by 2 into 2 pi n, the value of n is 1000 revolutions per minute, 2 pi into n by 60 square by g. I will put it as 9.8 into 10 raised to the power 2. This comes as 83.83. Similar problem in calculating the g factor. The true centrifugal casting is performed horizontally to make large diameter copper tube sections. The tubes have length 1.0 millimeter, diameter 0.25 millimeter, wall thickness as 15 millimeters. That means I have, I'll put it in the next slide. Length has 1 meter, then I have diameter as 0.25 meters, and the wall thickness, I'll call it as thickness T as 15 millimeters, right. Now it says if the rotational speed of pipe is 700 revolutions per minute, that means I have been given the rotational speed n. N is equal to 700 revolutions per minute. Then it says determine the g factor on the molten metal. This is part A. Part B is the rotational speed sufficient to avoid rain. What volume of molten metal must be poured into the mold to make the casting if solidification, shrinkage and contraction after the solidification are considered? Solidification shrinkage for copper is 4.5%, that is given, and its thermal contraction is 7.5%. So this is interesting. Now the problem says there is an internal dia, there is an external dia, and between them there is thickness. This is thickness T. This is our D outside, and this is our D inside. The outside is 0.25 meters. Thickness is given as 15 millimeters. Now, inner dia Di is equal to DO minus 2 times the thickness, which is equal to 0.25 minus thickness is in millimeters. I will convert that into meters. 2 into 15 into 10 raised to power minus 3. This gives me value of Di as 0.22 meters. Part A, that is G factor. G factor, again we can calculate using the same relation that we used in the previous problem, Fc by W. So G factor finally turns out to be R omega square by G. If I put all the values here, this is D outside by 2 into omega is 2 pi n by 60 by G. This is equal to 0.25 by 2 into 2 into 3.14, that is the value of pi, into n, that is 700 revolutions per minute. So this value of n is 700 is by 60 square by G. This gives me the G factor as 68.46. Second point, point B, is the rotation speed sufficient to avoid rain? Answer it here itself. Rotation speed, how do we say it is sufficient or not? There is a range in which it should lie. Optimal range is between 60 to 120. If it is between 60 to 120, we can say it is an optimal range here. So here what is the value? The value of the G factor is 68.46. So I will put it as point B. 60 is less than 68.46 is less than 120, it lies in the optimum range. Optimum range. Therefore, rain is avoided. So, this ensures that the molten metal adheres to the mold walls uniformly. It avoids defects caused by insufficient centrifugal force while preventing excessive force that might cause segregation or turbulence. Excessive force is not there. So, that means it stick to the walls proper and it will stay in the optimal range and it would fine, G factor. Now, third problem or the problem C here, that is, what volume of molten metal must be poured into the mold to make the casting if solidification, shrinkage and contraction after solidification are considered. So, solidification, shrinkage is given, thermal contraction is given in percentages. So, let me try to see this. So, volume of molten metal must be poured into the mold to make casting if solidification, shrinkage and contraction after solidification are considered. So, I have to say V is equal to final volume of product or volume of final product. This is equal to pi by 4 dO square minus di square into its length, which is equal to pi by 4 0.25 square minus 0.22 square into its length, that is 1. This is equal to 0.01107 millimeters cube. Solidification shrinkage, is 4.5% and contraction is 7.5%. So, V dash, that is the desired volume that should be poured into the mold to make the casting, considering both shrinkage and contraction, would be equal to the volume V that we have calculated, the final volume that is required, and the shrinkage and contraction has to be compensated. That means, we will say 1 minus shrinkage into 1 minus contraction. So, this is equal to 0.011074 by 1 minus 4.5 by 100 into 1 minus 7.5 by 100. This gives me the final volume as 0.012536 meter cube. So, this is the volume that is required so as the shrinkage and contraction is considered. It does not bring any cavity or any void space in the casting. So, with this I am closing this tutorial session. We will meet in the next lecture where I will talk about certain laboratory demonstration, the virtual laboratory demonstration in casting. Thank you.